All right, so let's talk about how we represent numbers and calculated / measured values in science. The first thing that you need to understand is that we use a very different set of measurement units or counting units than here that we do commonly in our vernacular in America. It's called SI, Standard International Units. I'm sure if any of you have taken physics or literally any other science class before this, you are used to this. So just a quick review, our three main base units that we'll work with in chemistry are mass in grams. And by the way, 1 gram, one amount of mass, one amount of substance is about equal to a paperclip. Then we'll work for when we quantify the characteristic of volume, we often work in liters or some scaled up, scaled down version of it. And finally, when we talk about length or distance, all right, we use meters. Should all sound familiar. Don't forget we use for metric, for really any type of unit, it doesn't have to be just metric. And actually, I'm gonna fix this. For scaling units, we use a prefix known as metric prefixes, but we can use them for basically any type of base unit. And there are many. They go from tera, which is 10 to the 12th. Okay, I don't even know how to count that number. I don't know the equivalent to billion. I don't know if it's like a gazillion or something, all the way down to tiny pico. And the whole idea of a base unit is it serves as the center, like kind of ground zero. This is where our base unit is. And then we can scale up or scale down from that. For scaling down, it goes right afterwards, deci for smaller. Okay. Then it goes to centi. Then it goes to milli. Ooh, gee willikers. Milli. Then it goes to micro, and so forth. I'm really not going to go over a ton of this because you guys can Google this / you should be pretty familiar. And then going up toward larger values, scaling up, we go to deca, not deca, sorry, deca, which you probably won't use very often at all. Hecto, which again is also slightly unfamiliar. And here's the main one, kilo. That's the big one, as well as mega. And then there are more values that you can proceed with. But each prefix has a specific scale value associated with it, as well as a symbol. I'm going to leave you guys to figure out in Google the respective symbols and values, scale values. So I'm just going to say Google / you guys should already be pretty familiar with this. So we use prefixes mainly as a tool for scaling up or down our values. And we can do this with multiple units. You'll actually see that when we measure something, we often measure in kilogram on the macro scale, right? Like our bodies well, here in America, we measure in pounds, but we would go by kilogram. Or you'll find that for smaller things, we often measure in the milli or centi. So like milligrams or centigrams. Okay. Quick note about units. We'll encounter many units in AP. We call a unit that's made of two different units combined a derived unit. So an example would be kilograms per second, okay, or miles per hour. Now, I know this right here is not an SI based unit, but it is a derived unit where we have 2 or more units, okay? It's composed of 2 or more units, 2+ units, okay? That's what a derived unit is. So moving on, scientific notation is a very specific way we write scaled up and scaled down numbers. I'm sure if you Googled or have ever Googled the metric prefixes, you will see this like weird kind of times 10 to the something setup, some value times 10 to the something. The purpose of scientific notation is to simply simplify writing very large or very small numbers. I'll say values to be more generic. So one great example and super important number that we encounter is Avogadro's number. Now, Avogadro's number in scientific notation is 6.022 times 10 to the 23rd. If we were to write that number, just expanded version, its original version, it would be that number. I don't even know how to say that number, okay? But obviously that is not a very useful way of expressing it, nor is it practical. So scientific notation is just the shortcut, okay? And it basically acknowledges anytime we have a bunch of trailing digit places, we will simplify that to a number between 1 and 10, okay? It has to be between 1 and 10, okay? And then add this times 10 to the value. And this right here is how much we move the decimal place. This number up here represents movement of decimal. So for Avogadro's number, since I am working with a huge number, I will have a positive exponent, which means I'm working with a large number. If I were to work with a small number, I would have a negative exponent, which means I'm working with a small number, okay? For Avogadro number, it's a huge number. I used, let's say we have this decimal over here. I moved it 23 times toward the left, and that's how I get 6.2. I moved it 23 times to the left in order to make a number between 6 and 10. And I simply follow the format, and there you go. If I were to flip that in the decimal, and I had many, many zeros for a very small decimal, it would become times 10 to the negative 23rd if I had the same digit placement movement. So go ahead and take a moment to do these practice problems. If you feel good, by the way, about this, you don't have to do the practice problems. It's totally up to you. All right, take a moment. All right, so hopefully you guys got the following values. Notice I kind of snuck in thinking about it in the reverse way. A really good way to test if you understand a concept, especially a mathematical, numerical based concept, is to go back and forth between how you approach solving the problem. So for the first two, we took an expanded form, an expanded notation of a value, and turned it in and represented it into scientific notation. And then for the last two, we did the opposite. We went from scientific notation to the expanded value. Notice a big thing is that the actual magnitude of the value, magnitude of the number does not change. That's the biggest thing. And that's why we love scientific notation. So moving on, you're welcome to try out more of these practice problems. And I'm going to go ahead and move on. In the filled notes upload, I will have the answers. All right, so let's talk about unit conversions and equivalence factors. Since we often in science and in general in life work with multiple different types of counters and units. For example, we often find ourselves converting from dollars to some other currency. Let's take, I don't even know what that is. I've just seen that symbol around. I think it's the won, if I'm correct. Let's say you're traveling, you often have to do conversion rates, right? Well, a very similar principle is done commonly in science, where we have to convert from one unit to another in order to answer a question or in order to complete a mathematical equation, in order to plug in the necessary variables. So we use what we call equivalence or conversion factors. And equivalences are simply numerical relationships between two units of equal value. So an example would be for every 4 quarters equals $1. I could write this as a fraction, by the way, hence the word conversion factor, fraction. I could say $1 is 4 quarters, or 4 quarters is $1, right? We work with this type of stuff all the time. The big thing is when we perform unit conversions going from one to another using equivalence or conversion factors, you must always cancel out your old units and have your desired units on top or in the proper location. So for example, if I am in a hot air balloon and my hot air balloon can hold 20 liters of air, how many milliliters of air can the balloon hold? So hopefully you are familiar with your prefixes, and you should immediately be able to identify we are using the common base unit of liters to talk about volume and scaling and converting between a scaled up and scaled down version. So we start with what we were given. I have 20 liters of air. Oh, specifically 20.0 liters of air. And I want to get to how many in milliliters. So what I do is I simply write a conversion factor and I identify, well, I know that for every 1 liter, I have 1,000 milliliters. That is equivalent to one another. Those are equal values in different units. Or I could say I have 1,000, gigaliters. Or I could say that for every 1,000 milliliters, I have 1 liter. You can decide. Now, if my goal is to end up in milliliters, I want to choose the conversion factor that has milliliters on top and allows me to cancel out my liters. So that would then make my mathematical process be 20.0 liters times, I'm going to choose this one, 1,000 milliliters over 1 liter. My liters cancel out and I get a value of 20,000 milliliters of air. All right, so that's a really simplified version. I'm going to trust that as you guys work through workbook problems, all right, you will be able to become a master in this. Quick note, when we have a value, a unit that's squared, often use like we use in the American system when we talk about architecture, square footage, looking at a house, we'll say 100 square feet, 100 cubic feet, right? It's really important that you recognize that your conversion factor also must be squared or cubed or raised to that whatever exponent of the final unit. So let's say I want to convert 2,600 centimeters cubed to millimeters, some value of millimeters cubed. All right. This might seem like, oh, easy. I know that I have for every 1 centimeter is 100 millimeter. Oh, gee, well, it's not 100. 10. Yikes. Millimeters. Okay. Millimeters is 1 scale, 1/10 degree smaller than a centimeter. Or I could say that for every 10 millimeters, I have 1 centimeter. Now I want to end up in millimeters, so I know I'm going to end up using this one. Now here is the catch. You might be tempted simply, and this is a super common mistake at even advanced APers, when they're in a rush, they make the mistake. You might be tempted to write 2,600 centimeters cubed times 10 millimeters, okay, and 1 centimeter, and then just multiply across. And you say, oh my gosh, that's 26,000. All right, 26,000 millimeters cubed. And suddenly you have a magical cubed. But that is so wrong, okay? Because you're not identifying or acknowledging the fact that you do have a cubed nature to your unit. So what you should do instead is you should instead write using your properly identified unit conversion. You have to cube this. So really what this becomes is 10 cubed millimeters, which is 1, 2, 3 cubed millimeters, all over 1 cubed centimeter. Now you have that, and that is the appropriate conversion rate, and you get a value of 2,603, all right, millimeters cubed, okay? So that's just a quick note. Let's skip over this. I moved this in your guys' PDF, but I want to move that down. We'll talk about that in the next video on uncertainty and sig figs, and go ahead and take a moment to do this practice problem. Oh, you know what's kind of funny? I was just looking at this practice problem, and this is also going to have to be moved down to after sig figs, or moved down into the sig fig lecture. Move down to sig fig. So sorry about that. Didn't catch that initially. Quickly then, let me just introduce a unique unit for temperature. Temperature doesn't necessarily have an SI unit that we scale up and scale down. It kind of is its own thing. But quick note, temperature is a measure of energy, by the way. Measure of energy, specifically like the kinetic energy of particles, all right, or some substance. Be careful to not mistake it as equal to heat. This will matter in a few units when we talk about the heat or enthalpy of a given system or reaction. It is not heat. And when we talk about the units for temperature, we use Fahrenheit, but scientifically, we tend to prefer to use Celsius or Kelvin. Celsius, you're pretty familiar with. Kelvin, though, might be a new one. Unless you've taken physics, you should have already worked with Kelvin. Kelvin is the only unit measurement for temperature that contains an absolute zero. So at 0 Kelvin, there means there's literally no motion of particles. Particles are always moving and generating energy, okay, which can produce heat, right? But at 0 Kelvin, there's absolute no motion, all right? I think there's only one natural incident where scientists have found a place on Earth / in Earth that is 0 Kelvin, where there's no particle movement. It's very, very hard to simulate. Also notice something, Kelvin does not have a degree sign, so be very careful. It is capital K for Kelvin. The conversion between Celsius and Kelvin is that some value Celsius is equal to the original value in Celsius. Oops, sorry. Let me actually hold on. Some value in Kelvin is equal to the original value in Celsius plus 273.15. That's the conversion between Kelvin and Celsius. Become very familiar with that. All right, guys, that's it for today. Good luck.